Assalamualaikum and good day everyone. In this video, we're going to continue with chapter 2. Specifically, in this video, we're going to cover memory organization, program counter and stack, and direct and indirect addressing. So in a microcontroller, the memory is used to store any information required to run the application. So this information can either be program, which can also be called as instruction, or data. So the difference between a program and data is that a program is a set of coding or instructions that we write. How about data? Data is the raw information that we usually use as operand in our instructions. For example, here we write our coding as human. So we write our code at 24:25. Okay, so this is just a simple example. Okay, so as human, we write this code. And then when this code is being translated for microcontroller to understand, so it will be translated into the binary form of it. Okay, so let's say this is the binary form of our instructions over here. So what happens is that this data, okay, which is directly converted from the instructions over here, this one is called as program. So this program will be stored inside the program memory. So how about data memory? So in this case, when the same instruction is being decoded, when it is being decoded, so it will translate its instruction into, so it will translate this instruction, into the command and also the data related to the command. Okay, so this data is the one that will be stored in data memory. Okay, so this is what we call as data information, and this is what we call as program information. So I hope by now all of us can differentiate between data and program. In PIC, a program or instructions is stored in the ROM or program memory. The data pula, okay, it can be stored either in RAM or in EEPROM data memory. So for RAM, it consists of two types of registers. The first one is called as general purpose register, okay, or GPR, and the second one is called as special function register or SFR. So what are the difference between these two? General purpose register, okay, we can use it to store any information, okay, or any data, because the name is general purpose. But for SFR, okay, so as the name implies, it is a special function register, isn't it? So the data has some special meaning to it, such as the registers that we had put before, that is trace A, trace B, port A, port B, status register. So these are all registers that fall under the special function register. So this special function register is not permanently safe, meaning that the data will be cleared when it is powered off. How about EEPROM data memory? So EEPROM data memory allows the data to be saved permanently. So the data can be changed during the operation of a microcontroller, and it consists of 64 locations with 8-bit wide each. And it is not directly addressable, but it can be accessed through these two registers, EEADR and EEDATA registers. So let's take a look at the internal architecture of PIC 16F84A. Okay, so here you can see this is the flash memory of PIC, in which this is the location in the internal architecture, which is called as a program memory. So here the notation here is 1K times 40. So it means that it has a 1 kilo space, 1024 space. Okay, and times 14 over here means that the size of each space is 14 bits. How about data memory? Okay, so for general purpose register, the location is here. Okay, so this is the general purpose register. So as you can see from the notation over here, so it has a 68 space, where each space can store 8 bits data. So this is what it meant by the notation over here. And then we have an EEPROM in this internal architecture. Okay, so EEPROM is also one of the data memory. So EEPROM, as the name implies, and as the notation given over here, so we know that it has 64 space, okay, where each space can store 8 bits data. So this is where the location of each of these memory in the internal architecture. And how about the special function register, isn't it? SFR. So SFR means special function register is scattered along inside this internal architecture. Okay, why is that? Because each register is mapped to the peripherals inside the device. Okay, for example, TMR0. Okay, so this is one of the registers, okay, which is related to the timing information inside the PIC. And then we have I/O ports registers, which are trace A, trace B, and then port A, port B. So all these registers is mapped to its input-output ports over here. So that's why the location is scattered inside this internal architecture. Okay, another one we can recognize over here is the status register, isn't it? So the location is somewhere inside here. But each of these space is mapped into its address. In fact, all the blocks over here, okay, all the blocks inside the internal architecture of the PIC is mapped to its address. Okay, so how do we know what is the address for each of these blocks? So this one we can look in the next slide. This is the illustration of the memory organization in our microcontroller PIC system FKEKK. So we look at the program memory first, as we can see from this figure. So each of the space in program memory has its own address, isn't it? So the address for the program memory starts from 000H until 1FFH. So this H at the end of the address over here actually tells us that the address, is in hexadecimal form. Okay, hexadecimal form. Alright. So if we calculate the address from 000 until 1FFF, so we can see that the total space is equals to 1024. Okay, try out. If you try to calculate this, then we can see the total space is 1024. And from the features of PIC, each of this space will store, okay, or can store 8 bits data. So why is that? Because each instruction, for example, move LW 0x54, for example, this instruction, okay, if, as a user or as a programmer, so we write this instruction and we program or we load this instruction into our microcontroller, isn't it? So what happens is that this instruction will be translated into its machine code, in which the length of the machine code is 14 bits. So each of these 14 bits is the one that will be stored in the program memory. Okay, so this is what it meant by this one. The program memory stores 1024 times 14 bits. And these instructions, okay, will be called one by one by program counter. Okay, so you can see here, PC stands for program counter. So this program counter is another register in PIC, in which it stores the address of the next instruction to be executed in the microcontroller. So here you can see that the size of the program counter is 13 bits, isn't it? So the size of the program counter, okay, the space that it has, okay, in this register is 13 bits. Okay, so why? Because if you see from the notation over here, okay, so kita macam ni kan, 12 lepas tu dot dot 0. So it means that it has 13 bits, okay, from bit 0 until bit 12, in which the total is equals to 13 bits. So these 13 bits store the address of the program counter. So if you look at the total length of the address over here, okay, so kita tengok total length ni, 1FFF. If we convert to its binary, okay, binary, so it's equals to what? 0001, 1111, 1111, 1111 kan? Kurang buat lagi. Okay, 1111 kan? So here ada 4, 4, 4. Okay, 12 bit kan, betul? Tambah 1. So 13 bit. So altogether there will be 13 bits. Okay, so why is that? Not why is that? Okay, so this is the maximum. Okay, maximum bits that it needs for the program counter to write the address, okay, inside its location, inside its space. Okay, so that's why the size of the program counter is 13 bits. Can you get that? Okay, so in other words, program counter is actually an address register. Okay, so why do we call it as address register? Because it stores address. Address of what? Address of the next instruction to be executed. Okay, so what can we learn here next? Okay, so location 0 in program counter 0000H is reserved for reset, while location 4 0004 is reserved for interrupt vector. Meaning that in our programming later on, the first instruction that we write will be stored in the reset location over here. Okay, and if let's say we enable interrupt in our program, okay, then the start of the program for the interrupt will be stored at this location first, 0004. Okay, so this one we will look from time to time, okay, but for now, just understand, just try to grab the information first, okay. So next we will look into other memory block. Next, we will look at the data memory. Okay, so recall that data memory has two types, isn't it? Either we store it in RAM or we store it in EEPROM. So we look at the EEPROM first. From the figure over here, so we can see that each space in EEPROM also has its own address. This, in other words, it starts from the location 00H until 3FH, isn't it? So 00H until 3FH. So if we calculate the total space that can be addressed through this range, okay, so the total space is equal to 64 space. Okay, and as we can see from the illustration over here, each space can store 8 bits data. So this is for EEPROM. And for us to access EEPROM as programmer, so we need to play around with these two registers, EE ADR and EE data register. Okay, so this one we will look into from time to time. Okay, but then for now, okay, what we need to understand is we need to know that the EEPROM, okay, has its own address and its space can store 8 bits data. So how about RAM? So recall that RAM has two types, isn't it? Either it is fall under general purpose register or special function register. Okay, so let's look at the next slide. So where is a special function register located in the memory organization? So it is located in the first 12 location in bank 0 and bank 1 of the memory location. So as you can see here, this is the we can say that this is the RAM. So the address starts from 00 until FFH. But then for special function register, the address starts from 00 until 0BH in bank 0 and 80H until 8BH in bank 1. So this is what we call as a special function registers. So as you can see over here, each of these space has its own name, because it's a special function register, and this name is related or coupled with the internal architecture of the PIC. And each of these space can store 8 bits data. Okay, or in other words, the space of each of these location is 8 bits wide. Okay, maksudnya size dia 8 bit lah, 8 bit. And then for us as designer to access the registers SFR ni, okay, during program writing, we need to select the bank in which it contains the register. Okay, so in our programming later on, if let's say we want to access port A register, for example, so we have to select first the bank in which the register resides. Okay, so this is what we meant by this line. How about general purpose register? Okay, so general purpose register pula falls at this location from 0CH until 4FH. Okay, so if we calculate this location, the size is equals to 68 space. Okay, so this one you can try out. Okay, try to calculate the size. Okay, so dia sama dengan 68 space. So each of these space sama, dia boleh store 8 bits data. Right, and then okay, how about location 8CH and CFH ni? Sebab dia semua label under general purpose register label kan. Okay, so this location actually doesn't have any meaning, okay, because if we access this location, we are accessing the same location in bank 0. So in other words, sebenarnya sama je lah, bank 0 ke bank 1 ke, as long as we access this location, so both will point to the same space. So for GPR, if I say we want to use it to store our data, we no need to worry about the bank location, okay, because either address will point to the same data. This slide summarizes the general purpose register and special function registers information. So as a reminder, to access any special function registers requires us to do the correct setting of the bank select information. Otherwise, the incorrect information might be entered or gathered. Okay, so another thing is that the special function register, its function is predetermined during the manufacturing process. Okay, whereas for general purpose register, so it is used for storing temporary data and results during the operation. Okay, so this is just a repetition. Let's take a look at the program counter. So as we have seen before, program counter is a register that contains the address of all locations of the instructions to be executed at the current time, isn't it? So that is program counter. And from the figure over here, so we know program counter size, the size of the register is 13 bits. This is the program counter, the size of the register is 13 bits. Okay, so what happened is that, okay, so there are 13 bits value inside the program counter. So let's say 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. So what happens is that physically, with these values is being stored in two types of special function registers over here, called as PCLAF and PCL. Okay, so the lower 8 bits over here will be stored in PCL, and the higher 5 bits over here will be stored in PCLAF. Okay, so these two are special function registers. So this is a special function registers, PCLAF and PCL. Okay, and this is what happened. So other information about program counter is that when the computer restarts or resets, the program counter will normally reverts to 0, meaning that when the device or when the PIC is restart or reset, okay, so program counter will always point to 0000H location. And other than that is that once it holds the first value, okay, and then when the instructions is being fetched, the program counter will automatically point to the next instructions in sequence, meaning that if let's say at the current moment PC value is equal to 0000H, okay, so after this instruction is being fetched, then the program counter, okay, will increment its value to 0001H. So this one happens automatically. Okay, automatically, once each of the instructions have been fetched, so the program counter will automatically change its value by adding 1 to the previous address. Okay, so if let's say this next instruction is again being fetched, okay, then the program counter will hold the next value 2 and so on and so forth. Okay, so this is what happened. Okay, how about stack? Stack is actually another address register. Okay, another address register in which it keeps the value of program counter after a jump from the main program to an address of a subprogram. So in other words, we know that program counter usually increment itself to point to the next location in the program memory, isn't it? Okay, for example, let's say the current location is 0005H. So after the instructions in this location is being fetched, then the program counter will increment itself to the next location in the program memory, isn't it? Which is a 0006. And then what happened is that the next instruction also is being fetched. Okay, fetch. And then the program counter will increment itself. Okay, let's say at location 0007H. Okay, there's in this location, okay, the instructions being written at this location is let's say call some subroutine. Okay, let's say call LEDX, for example. Okay, for example. So this LEDX, if let's say the location of this subroutine, let's say the location is at 0020H in program memory. So what happens is that after the instruction at the 0007 is being fetched, the program counter will not increment itself to 0008, but it will change its value, okay, to the location that is being written in the instructions call just now. Okay, so now the new value for the program counter will be 0020H. Okay, because what happens is that because it needs to serve, okay, the call instruction just now. So then it will look into this location. Okay, the instruction over here will be fetched and then executed. Okay, and then the program counter will increase itself with one value. Okay, until and then this instruction also being fetched. Once it is fetched, then the program counter will increase itself to point to the next value in the program memory until it comes across instructions. So let's say at location 0028H. The instructions here is let's say return. So usually the instructions call and return is like coupled. Okay, so once we call, so we need to return. So once the program counter come across this instruction return, let's say this instruction is being stored in location 0028H. So now what happens is the program counter will look at the address in which it left the original flow just now, which is the value at 0008H. Okay, so by right, it should flow from 005 to 07 and then 8 and so on and so forth, isn't it? But then it detour from the main flow because of the call instructions. Okay, and then once it goes to the call instructions and then serve everything, and suddenly it comes across the instructions return. So when it comes across the instruction return over here, what happens is the program counter will look back for the previous address in which it left its original flow. Okay, so how do we know that how do the PIC know it needs to go to the address 0008 upon return? Okay, so this address is the one that is stored in stack just now. Okay, when the program counter left its original flow and then goes to serve the subroutine just now, the instruction that is supposed to execute, which is located at 0008H. Okay, so the address of that instruction is being stored in stack. Okay, so in stack. So this is the space of stack. So stack has 8 levels. So meaning that it has maximum 8 program calls or interrupts. And how does it behave? So it behaves respectively. Okay, when it comes across the instructions call, then the stack will be pushed inside. The stack is the address. The address will be pushed inside the stack, and then if it comes across the instructions return, read LW and read P, then what happens is that the address will be popped from the stack. Okay, so this one we can look at. The next slide over here. So this is the illustration. If let's say the program counter encounter instructions in which it needs to serve a new address which is out of the flow. Okay, then the address that is supposed to serve will be pushed in the stack. Okay, so let's say address 1 over here will be pushed in the stack, and then somehow when the program counter continues its operation, okay, let's say it comes across another instructions that cause the address to be pushed in the stack as well. So then the address will be pushed inside the stack until maximum it can hold until it addresses. It addresses. So because if let's say the program counter come across another instruction to cause it to detour from its original route. Okay, so what happens is the new address will be pushed at the latest location over here. Okay, and the last address, the first address that is being pushed before will be um, will be discarded. Okay, you can say that will be discarded because the total address space for the stack is only 8 space. Okay, 8 space here. Okay, so this is how the mechanism looks like. Okay, let's take a look at pop pula. So let's say in the microcontroller system, okay, and then the program counter comes across instructions in which it needs to return to the previous state. Okay, so what happens is that the latest value of address in the stack will be loaded inside the program counter. Okay, and then once this address has been loaded in the program counter, then the program counter will continue its operation. Let's say somehow it comes across another instructions that cause the program counter to refer to the stack, okay, to return to its flow value. to the original flow. Then what happened is the latest address available in the stack will be popped up. Okay, and then program counter will serve the whatever it is instruction that is being written in the address 2 lah. Okay, and then if let's say come across another instruction that cause the the stack to be popped up, okay, then this is what happened. The program counter will look into the stack for the last instructions available in the stack. Okay, so this is how the mechanism looks like. Okay, so that's it about stack. Now we're going to look at addressing. Okay, so what is addressing? Addressing is a concept or term referring to how the microcontroller knows which location to access from the instructions that we write. So there are two modes of addressing. The first one is called as direct addressing. The second one is called as indirect addressing. So any access to special function registers is called as direct addressing. Okay, so how does the microcontroller derive the address location in which it needs to access? Okay, so it depends on the instructions itself. Okay, for example, if let's say we write instructions move WF trees B. Okay, so in this case, it says that we need to move whatever it is that is whatever data that is inside W register into trees B register. Okay, so we need to move into trees B. So now these instructions cause the microcontroller to access trees B location. So what happens is that the address will be derived from 2 bits. 2 bits from the status register, bit RP0 and bit RP1. So this is supposed to be RP0, RP0. So bit RP0 and RP1. So bit RP0 and RP1, this one will indicate which bank does the special function register resides. Okay, so that's the first one. And which register we need to access, that one we can get from the 7 bits from the instructions, which actually shows the location of the trees B in this example. Okay, for example, trees B, the location from the memory organization. So we know trees B is located at location 06, isn't it? Okay, or 06 or 05. Okay, let me check first. So the location is trees B, sorry. Okay, trees B located at 86. Okay, trees B located at 86H. Okay, so then what happens is that this address, okay, will be translated into its binary bits, okay, which is 81000. 6 is equals to 0110, isn't it? Okay, so this is the location, the address. So this 7 bits, these 7 bits will be loaded into this address 000 and then 110. So this is the address, and then the address in front over here will indicate which bank does the frisbee resides. Okay, so how do we know this? So this is through programming as well. So usually we will add another instructions before we access the frisbee, okay, to indicate which bank to select. Okay, bank select. So from this information, then the values inside RP1 and not RP1, RP0 lah. So RP1 and IRP ni is unimplemented in status register. So the values that will change is RP0. Okay, so RP0, if let's say the value is 0, then meaning that we are accessing bank 0. If the value is 1, then we are accessing bank 1. So this one is derived from the previous instructions, okay, about bank select. So in this case, 01 lah, 01. So from this 9-bit address, then the microcontroller knows which location to access to get to trees B. Okay, so this is what we call as direct addressing. So let's take a look at the next one. what we call as indirect addressing. Indirect addressing is a mode used by PIC to access the location in the general purpose register. So recall that we have a special function register and general purpose register, isn't it? So general purpose register is the memory or data memory located in space 0C until 4F, isn't it? Okay, so if you can still recall, so this is the location over here. Okay, so if the microcontroller wants to access this location, it needs to use indirect addressing. Okay, so how to do that? We need to make use of these two registers, INDF register and FSR register. So why can't we use direct addressing when we want to access this general purpose register? So because in instructions inside PIC, so the instructions is being designed such that it needs to call the name of the registers to deal with the registers directly. But then for the general purpose register, each of these locations doesn't have a specific name, isn't it? So that's why we need to use indirect addressing if we want to access any of these locations. Okay, so how to do that? Okay, so FSR is a short form for file select register. Okay, file select register. So it also acts like a pointer, So first what we need to do is we need to load this register with the address that we want to access. For example, if I say we want to access location 0x20, okay, which is somewhere over here, isn't it? 0x20. So first we need to load this address into FSR. So that one we can use these two instructions. And then let's say we want to actually clear the bit value inside this register, okay, inside this location, 20 location. Let's say we want to clear the value inside. Okay, so how to do that? So we use the next instruction over here, which is clear register, okay, and then we call INDF register. INDF is the indirect register. So whenever we use this INDF register, okay, so it's actually calling, okay, ataupun pointing to the address written in the FSR. So these two registers are related, FSR and INDF. So whenever in our instructions, if we deal with INDF, so it's actually talking with the values stored in the FSR. So in other words, for clear CLRF INDF, these instructions, this one says that clear register INDF. So what happens is that the microcontroller will look inside FSR, okay, and then it will read the value inside FSR. In this case, we have stored 20 just now, isn't it? So then what happens is that it will go to this address, okay, 0x20, which is inside at the general purpose register, and then it will clear, okay, clear this register. So this is what it meant by clear RF INDF. So if let's say we want to give some value, okay, inside the location in GPR, we want to directly give the value. Okay, so we can use this INDF register, okay, to address our general purpose registers location. But before we can do that, so we have to load, okay, load our FSR, okay, with the correct address of our GPR that we want to access. Okay, so depends on which location that we want to access. So we have to put this value inside this FSR first. Then only we can call it by using the INDF. So this is what we call as indirect addressing. Okay, so as you can see over here, so this is how the address is being derived by the microcontroller. Okay, so what happens is that the microcontroller will look at the 7 bits inside FSR to derive the address of the location to be accessed. Okay, so in this case, if let's say we have an address in hexa 20, okay, so in binary is equals to 000, 0010, and then 0000, isn't it? but then this address will only take 7 bits. Okay, so here we'll have 0, 1, 0, okay, and then 0, 0, 0, 0, and then the IRP bits over here, because our PIC is a PIC 16F84A, isn't it? So the bit IRP, okay, in status register is unimplemented. Okay, so this value will always be 0. Okay, so then the address point by the FSR will always go to the location point at bank 0. Okay, so this is for our PIC. Alright, so I hope you can get this. So if let's say we load the FSR with address that is located somewhere here in bank 1, isn't it? Okay, so if let's say we accidentally write address which is located at bank 1, still the location that will be accessed is the one that is located in bank 0. Okay, so this is the case for our general purpose register. If you can still recall this kind of information we had mentioned in the memory organization part. Okay, memory organization part. Okay, so I guess that's it for this part. Okay, so basically in this video we had covered the the memory organization, program memory and data memory, and then we had covered the program counter and stack, and also direct and indirect addressing. Okay, so oscillator, and then clock, instruction cycle, and pipelining, timer, and interrupt and polling. So this one we covered already during our online class on Friday. Okay, so if you still remember. So in order to revise on this, so please access the video recording that I had shared in our ULearn. Alright class, so with that, thank you for your attention. I hope you get the essence of this course, and if you have any questions, just let me know during our online session. Hopefully everything is good for you. Okay, so thank you.